Chapter 8, Part 6 of Airplane Flying Handbook, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Norman Ilver. Airplane Flying Handbook, Volume 1 by Federal Aviation Administration. Faulty Approaches and Landings. Low Final Approach. When the base leg is too low, insufficient power is used, landing flaps are extended prematurely, or the velocity of the wind is misjudged. Sufficient altitude may be lost, which will cause the airplane to be well below the proper final approach path. In such a situation, the pilot would have to apply considerable power to fly the airplane at an excessively low altitude up to the runway threshold. When it is realized the runway will not be reached unless appropriate action is taken, power must be applied immediately to maintain the airspeed, while the pitch attitude is raised to increase lift and stop the descent. When the proper approach path has been intercepted, the correct approach attitude should be reestablished and the power reduced and a stabilized approach maintained. Figure 8-31. Do not increase the pitch attitude without increasing the power, since the airplane will decelerate rapidly and may approach the critical angle of attack and stall. Do not retract the flaps. This will suddenly decrease lift and cause the airplane to sink more rapidly. If there is any doubt about the approach being safely completed, it is advisable to execute an immediate go-around. High final approach. When the final approach is too high, lower the flaps as required. Further reduction in power may be necessary, while lowering the nose simultaneously to maintain approach airspeed and steepen the approach path. Figure 8-32. When the proper approach path has been intercepted, adjust the power as required to maintain a stabilized approach. When steepening the approach path, however, care must be taken that the descent does not result in an excessively high sink rate. If a high sink rate is continued close to the surface, it may be difficult to slow to a proper rate prior to ground contact. Any sink rate in excess of 800 to 1,000 feet per minute is considered excessive. A go-around should be initiated if the sink rate becomes excessive. Slow final approach. When the airplane is flown at a slower than normal airspeed on the final approach, the pilot's judgment of the sink rate, descent, and the height of round-out will be difficult. During an excessively slow approach, the wing is operating near the critical angle of attack, and, depending on the pitch attitude changes and control usage, the airplane may stall or sink rapidly, contacting the ground with a hard impact. Whenever a slow-speed approach is noted, the pilot should apply power to accelerate the airplane and increase the lift to reduce the sink rate and to prevent a stall. This should be done while still at a high enough altitude to establish the correct approach airspeed and attitude. If too slow and too low, it is best to execute a go-around. Use of power. Power can be used effectively during the approach and round-out to compensate for errors in judgment. Power can be added to accelerate the airplane to increase lift without increasing the angle of attack. Thus, the descent can be slowed to an acceptable rate. If the proper landing attitude has been attained and the airplane is only slightly high, the landing attitude should be held constant and sufficient power applied to help ease the airplane onto the ground. After the airplane has touched down, it will be necessary to close the throttle so the additional thrust and lift will be removed and the airplane will stay on the ground. High round-out. Sometimes when the airplane appears to temporarily stop moving downward, the round-out has been made too rapidly and the airplane is flying level, too high above the runway. Continuing the round-out would further reduce the airspeed, resulting in an increase in angle of attack to the critical angle. This would result in the airplane stalling and dropping hard onto the runway. To prevent this, the pitch attitude should be held constant until the airplane decelerates enough to again start descending. Then the round-out can be continued to establish the proper landing attitude. This procedure should only be used when there is adequate airspeed. It may be necessary to add a slight amount of power to keep the airspeed from decreasing excessively and to avoid losing lift too rapidly. Although the back elevator pressure may be relaxed slightly, the nose should not be lowered any perceptible amount to make the airplane descend when fairly close to the runway, unless some power is added momentarily. The momentary decrease in lift that would result from lowering the nose and decreasing the angle of attack may be so great that the airplane might contact the ground with the nose wheel first, which could collapse. When the proper landing attitude is attained, the airplane is approaching a stall because the airspeed is decreasing and the critical angle of attack is being approached, even though the pitch attitude is no longer being increased. Figure 8-33. It is recommended that a go-around be executed anytime it appears the nose must be lowered significantly or that the landing is in any other way uncertain. Late or rapid round-out. Starting the round-out too late or pulling the elevator control back too rapidly to prevent the airplane from touching down prematurely can impose a heavy load factor on the wing and cause an accelerated stall. Suddenly increasing the angle of attack and stalling the airplane during a round-out is a dangerous situation, since it may cause the airplane to land extremely hard on the main landing gear and then bounce back into the air. As the airplane contacts the ground, the tail will be forced down very rapidly by the back elevator pressure and by inertia acting downward on the tail. Recovery from this situation requires prompt and positive application of power prior to occurrence of the stall. This may be followed by a normal landing if sufficient runway is available. Otherwise, the pilot should execute a go-around immediately. If the round-out is late, the nose wheel may strike the runway first, causing the nose to bounce upward. No attempt should be made to force the airplane back onto the ground. A go-around should be executed immediately. Floating during round-out. If the airspeed on final approach is excessive, it will result in the airplane floating. Figure 8-34. Before the touchdown can be made, the airplane may be well past the desired landing point and the available runway may be insufficient. When diving in an airplane on final approach to land at the proper point, there will be an appreciable increase in airspeed. The proper touchdown attitude cannot be established without producing an excessive angle of attack and lift. This will cause the airplane to gain altitude or balloon. Anytime the airplane floats, judgment of speed, height, and sink rate must be especially acute. The pilot must smoothly and gradually adjust the pitch attitude as the airplane decelerates to touchdown speed and starts to settle, so the proper landing attitude is attained at the very moment of touchdown. The slightest error in judgment and timing will result in either ballooning or bouncing. The recovery from floating will depend on the amount of floating and the effect of any crosswind, as well as the amount of runway remaining. Since prolonged floating utilizes considerable runway length, it should be avoided, especially on short runways or in strong crosswinds. If the landing cannot be made on the first third of the runway, or the airplane drifts sideways, the pilot should execute a go-around. Ballooning during round-out. If the pilot misjudges the rate of sink during a landing and thinks the airplane is descending faster than it should, there is a tendency to increase the pitch attitude and angle of attack too rapidly. This not only stops the descent, but actually starts the airplane climbing. This climbing during the round-out is known as ballooning. Figure 8-35. Ballooning can be dangerous because the height above the ground is increasing and the airplane may be rapidly approaching a stalled condition. The altitude gained in each instance will depend on the airspeed or the speed with which the pitch attitude is increased. When ballooning is slight, a constant landing attitude should be held and the airplane allowed to gradually decelerate and settle onto the runway. Depending on the severity of ballooning, the use of throttle may be helpful in cushioning the landing. By adding power, thrust can be increased to keep the airspeed from decelerating too rapidly, and the wings from suddenly losing lift. But throttle must be closed immediately after touchdown. Remember that torque can be created as power is applied. Therefore, it will be necessary to use rudder pressure to keep the airplane straight as it settles onto the runway. When ballooning is excessive, it is best to execute a go-around immediately. Do not attempt to salvage the landing. Power must be applied before the airplane enters a stalled condition. The pilot must be extremely cautious of ballooning when there is a crosswind present, because the crosswind correction may be inadvertently released or it may become inadequate. Because of the lower airspeed after ballooning, the crosswind affects the airplane more. Consequently, the wing will have to be lowered even further to compensate for the increased drift. It is imperative that the pilot make certain that the appropriate wing is downed and that directional control is maintained with opposite rudder. If there is any doubt or the airplane starts to drift, execute a go-around. Bouncing during touchdown. When the airplane contacts the ground with a sharp impact as the result of an improper attitude or an excessive rate of sink, it tends to bounce back into the air. Though the airplane's tires and shock struts provide some springing action, the airplane does not bounce like a rubber ball. Instead, it rebounds into the air because the wing's angle of attack was abruptly increased, producing a sudden addition of lift. Figure 8-36. The abrupt change in angle of attack is a result of the inertia instantly forcing the airplane's tail downward when the main wheels contact the ground sharply. The severity of the bounce depends on the airspeed at the moment of contact and the degree to which the angle of attack or pitch attitude was increased. Since a bounce occurs when the airplane makes contact with the ground before a proper touchdown attitude is attained, it is almost invariably accompanied by the application of excessive back elevator pressure. This is usually the result of the pilot realizing too late that the airplane is not in the proper attitude and attempting to establish it just as a second touchdown occurs. The corrective action for a bounce is the same as for ballooning and similarly depends on its severity. When it is very slight and there is no extreme change in the airplane's pitch attitude, a follow-up landing may be executed by applying sufficient power to cushion the subsequent touchdown and smoothly adjusting the pitch to the proper touchdown attitude. In the event a very slight bounce is encountered while landing with a crosswind correction must be maintained while the next touchdown is made. Remember that since the subsequent touchdown will be made at a slower airspeed, the upwind wing will have to be lowered even further to compensate for drift. Extreme caution and alertness must be exercised anytime a bounce occurs, but particularly when there is a crosswind. Inexperienced pilots will almost invariably release the crosswind correction. When one main wheel of the airplane strikes the runway, the other wheel will touch down immediately afterwards, and the wings will become level. Then, with no crosswind correction, as the airplane bounces, the wind will cause the airplane to roll with the wind, thus exposing even more surface to the crosswind and drifting the airplane more rapidly. When a bounce is severe, the safest procedure is to execute a go-around immediately. No attempt to salvage the landing should be made. Full power should be applied while simultaneously maintaining directional control and lowering the nose to a safe climb attitude. The go-around procedure should be continued even though the airplane may descend and another bounce may be encountered. It would be extremely foolish to attempt a landing from a bad bounce, since airspeed diminishes very rapidly in the nose-high attitude, and a stall may occur before a subsequent touchdown could be made. Porpoising. In a bounced landing that is improperly recovered, the airplane comes in nose first, setting off a series of motions that imitate the jumps and dives of a porpoise, hence the name. Figure 8-37. The problem is improper airplane attitude at touchdown, sometimes caused by inattention, not knowing where the ground is, mistrimming, or forcing the airplane onto the runway. Ground effect decreases elevator control effectiveness and increases the effort required to raise the nose. Not enough elevator or stabilator trim can result in a nose-low contact with the runway and a porpoise develops. Porpoising can also be caused by improper airspeed control. Usually, if an approach is too fast, the airplane floats, and the pilot tries to force it on the runway when the airplane still wants to fly. A gust of wind, a bump in the runway, or even a slight tug on the control wheel will send the airplane aloft again. The corrective action for a porpoise is the same as for a bounce and similarly depends on its severity. When it is very slight and there is no extreme change in the airplane's pitch attitude, a follow-up landing may be executed by applying sufficient power to cushion the subsequent touchdown and smoothly adjusting the pitch to the proper touchdown attitude. When a porpoise is severe, the safest procedure is to execute a go-around immediately. In a severe porpoise, the airplane's pitch oscillations can become progressively worse until the airplane strikes the runway nose first with sufficient force to collapse the nose gear. Pilot attempts to correct a severe porpoise with flight control and power inputs will most likely be untimely and out of sequence with the oscillations and only make the situation worse. No attempt to salvage the landing should be made. Full power should be applied while simultaneously maintaining directional control and lowering the nose to a safe climb attitude. Wheelbarrowing. When a pilot permits the airplane weight to become concentrated about the nose wheel during the takeoff or landing roll, a condition known as wheelbarrowing will occur. Wheelbarrowing may cause loss of directional control during the landing roll because braking action is ineffective, and the airplane tends to swerve or pivot on the nose wheel, particularly in crosswind conditions. One of the most common causes of wheelbarrowing during the landing roll is a simultaneous touchdown of the main and nose wheel with excessive speed, followed by the application of forward pressure on the elevator control. Usually the situation can be corrected by smoothly applying back elevator pressure. However, if wheelbarrowing is encountered and runway and other conditions permit, it may be advisable to promptly initiate a go-around. Wheelbarrowing will not occur if the pilot achieves and maintains the correct landing attitude, touches down at the proper speed, and gently lowers the nose wheel while losing speed on rollout. If the pilot decides to stay on the ground rather than attempt a go-around, or if directional control is lost, the throttle should be closed and the pitch attitude smoothly but firmly rotated to the proper landing attitude. Raise the flaps to reduce lift and to increase the load on the main wheels for better braking action. Hard landing. When the airplane contacts the ground during landings, its vertical speed is instantly reduced to zero. Unless provisions are made to slow this vertical speed and cushion the impact of touchdown, the force of contact with the ground may be so great that it could cause structural damage to the airplane. The purpose of pneumatic tires, shock-absorbing landing gears, and other devices is to cushion the impact and to increase the time in which the airplane's vertical descent is stopped. The importance of this cushion may be understood from the computation that a 6-inch freefall on landing is roughly equal to a 340 foot per minute descent. Within a fraction of a second, the airplane must be slowed from this rate of vertical descent to zero without damage. During this time, the landing gear, together with some aid from the lift of the wings, must apply whatever force is needed to counteract the force of the airplane's inertia and weight. The lift decreases rapidly as the airplane's forward speed is decreased, and the force on the landing gear increases by the impact of touchdown. When the descent stops, the lift will be practically zero, leaving the landing gear alone to carry both the airplane's weight and inertia force. The load imposed at the instant of touchdown may easily be 3 or 4 times the actual weight of the airplane, depending on the severity of contact. Touchdown in a drift or crab. At times the pilot may correct for wind drift by crabbing on the final approach. If the round out and touchdown are made while the airplane is drifting or in a crab, it will contact the ground while moving sideways. This will impose extreme side loads on the landing gear and, if severe enough, may cause structural failure. The most effective method to prevent drift in primary training airplanes is the wing-low method. This technique keeps the longitudinal axis of the airplane aligned with both the runway and the direction of motion throughout the approach and touchdown. There are 3 factors that will cause the longitudinal axis and the direction of motion to be misaligned during the touchdown: drifting, crabbing, or a combination of both. If the pilot has not taken adequate corrective action to avoid drift during a crosswind landing, the main wheel's tire tread offers resistance to the airplane's sideward movement in respect to the ground. Consequently, any sidewise velocity of the airplane is abruptly decelerated, with the results that the inertia force is as shown in Figure 8-38. This creates a moment around the main wheel when it contacts the ground, tending to overturn or tip the airplane. If the windward wingtip is raised by the action of this moment, all the weight and shock of landing will be borne by one main wheel. This could cause structural damage. Not only are the same factors present that are attempting to raise a wing, but the crosswind is also acting on the fuselage surface behind the main wheels, tending to yaw, weather vane the airplane into the wind. This often results in a ground loop. Ground loop. A ground loop is an uncontrolled turn during ground operation that may occur while taxiing or taking off, but especially during the after-landing roll. Drift or weather vaning does not always cause a ground loop, although these things may cause the initial swerve. Careless use of the rudder, or an uneven ground surface, or a soft spot that retards one main wheel of the airplane may also cause a swerve. In any case, the initial swerve tends to make the airplane ground loop, whether it is a tail wheel or a nose wheel type. Figure 8-39. Nose wheel type airplanes are somewhat less prone to ground loop than tail wheel type airplanes. Since the center of gravity, CG, is located forward of the main landing gear on these airplanes, anytime a swerve develops, centrifugal force acting on the CG will tend to stop the swerving action. If the airplane touches down while drifting or in a crab, the pilot should apply aileron toward the high wing and stop the swerve with the rudder. Brakes should be used to correct for turns or swerves only when the rudder is inadequate. The pilot must exercise caution when applying corrective brake action because it is very easy to over-control and aggravate the situation. If brakes are used, sufficient brake should be applied on the low wing wheel outside of the turn to stop the swerve. When the wings are approximately level, the new direction must be maintained until the airplane has slowed to taxi speed or has stopped. In nose wheel airplanes, a ground loop is almost always a result of wheelbarrowing. The pilot must be aware that even though the nose wheel type airplane is less prone than the tail wheel type airplane, virtually every type of airplane, including large multi-engine airplanes, can be made to ground loop when sufficiently mishandled. Wing rising after touchdown. When landing in a crosswind, there may be instances when a wing will rise during the after-landing roll. This may occur whether or not there is a loss of directional control, depending on the amount of crosswind and the degree of corrective action. Anytime an airplane is rolling on the ground in a crosswind condition, the upwind wing is receiving a greater force from the wind than the downwind wing. This causes a lift differential. Also, as the upwind wing rises, there is an increase in the angle of attack, which increases lift on the upwind wing, rolling the airplane downwind. When the effects of these two factors are great enough, the upwind wing may rise even though directional control is maintained. If no correction is applied, it is possible that the upwind wing will rise sufficiently to cause the downwind wing to strike the ground. In the event a wing starts to rise during the landing roll, the pilot should immediately apply more aileron pressure toward the high wing and continue to maintain direction. The sooner the aileron is applied, the more effective it will be. The further a wing is allowed to rise before taking corrective action, the more airplane surface is exposed to the force of the crosswind. This diminishes the effectiveness of the aileron. Hydroplaning. Hydroplaning is a condition that can exist when an airplane is landed on a runway surface contaminated with standing water, slush, and/or wet snow. Hydroplaning can have serious adverse effects on ground controllability and braking efficiency. The three basic types of hydroplaning are dynamic hydroplaning, reverted rubber hydroplaning, and viscous hydroplaning. Any one of these three can render an airplane partially or totally uncontrollable anytime during the landing roll. Dynamic hydroplaning. Dynamic hydroplaning is a relatively high-speed phenomenon that occurs when there is a film of water on the runway that is at least 1/10 inch deep. As the speed of the airplane and the depth of the water increase, the water layer builds up an increasing resistance to displacement, resulting in the formation of a wedge of water beneath the tire. At some speed, termed the hydroplaning speed, VP, the water pressure equals the weight of the airplane and the tire is lifted off the runway surface. In this condition, the tires no longer contribute to directional control and braking action is nil. Dynamic hydroplaning is related to tire inflation pressure. Data obtained during hydroplaning tests have shown that the minimum dynamic hydroplaning speed, VP, of a tire to be 8.6 times the square root of the tire pressure in pounds per square inch, PSI. For an airplane with a main tire pressure of 24 pounds, the calculated hydroplaning speed would be approximately 42 knots. This is important to note that the calculated speed referred to above is for the start of dynamic hydroplaning. Once hydroplaning has started, it may persist to a significantly slower speed depending on the type being experienced. Reverted rubber hydroplaning. Reverted rubber, steam hydroplaning, occurs during heavy braking that results in a prolonged locked-wheeled skid. Only a thin film of water on the runway is required to facilitate this type of hydroplaning. The tire skidding generates enough heat to cause the rubber to contact with the runway to revert to its original uncured state. The reverted rubber acts as a seal between the tire and the runway, and delays the water exit from the tire footprint area. The water heats and is converted to steam, which supports the tire off the runway. Reverted rubber hydroplaning frequently follows an encounter with dynamic hydroplaning, during which time the pilot may have the brakes locked in an attempt to slow the airplane. Eventually, the airplane slows enough to where the tires make contact with the runway surface and the airplane begins to skid. The remedy for this type of hydroplane is for the pilot to release the brakes and allow the wheels to spin up and apply moderate braking. Reverted rubber hydroplaning is insidious in that the pilot may not know when it begins, and it can persist to very slow ground speeds, 20 knots or less. Viscous hydroplaning. Viscous hydroplaning is due to the viscous properties of water. A thin film of fluid, no more than 1/1000th of an inch in depth, is all that is needed. The tire cannot penetrate the fluid, and the tire rolls on top of the film. This can occur at much slower speed than dynamic hydroplane, but requires a smooth or smooth-acting surface such as asphalt or a touchdown area coated with accumulated rubber of past landings. Such a surface can have the same coefficient of friction as wet ice. When confronted with the possibility of hydroplaning, it is best to land on a grooved runway if available. Touchdown speed should be as slow as possible, consistent with safety. After the nose wheel is lowered to the runway, moderate braking should be applied. If deceleration is not detected and hydroplaning is suspected, the nose should be raised and aerodynamic drag utilized to decelerate to a point where the brakes do become effective. Proper braking technique is essential. The brakes should be applied firmly until reaching a point just short of a skid. At the first sign of a skid, the pilot should release brake pressure and allow the wheels to spin up. Directional control should be maintained as far as possible with the rudder. Remember that in a crosswind, if hydroplaning should occur, the crosswind will cause the airplane to simultaneously weather vane into the wind as well as slide downwind. End of Chapter 8.